Pop quiz. What has 2 thumbs and is guaranteed to help you pass physical science? This guy. Enough with the cheesy jokes. Let's look at a photoelectric effect past paper question. Question 10 says, an investigation is done to determine the effect of the power of a light bulb on the current which is generated in a photoelectric cell. The apparatus used in this investigation is shown in the simplified diagram below. Ultraviolet light of wavelength 490 nanometers emitted by 2 bulbs A and B is shone onto the cathode of the photoelectric cell, and the maximum speed of the ejected photoelectrons is then measured. We can see the diagram there with a UV light source, the photoelectric cell, and the circuit that comes thereafter. We're then told the results of their investigation are shown on the table below. 10.1 then says, describe the term photoelectric effect. Now, this is a very easy one. Photoelectric effect is the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. Nice and easy. Let's quickly put the answer down together. All right, let's do 10.2. 10.2 then says, briefly explain why the power of the light bulbs does not affect the maximum speed of the ejected photoelectrons. Now remember, what does the power tell us about? The power tells us more around how much light is going to be emitted, right? Rather than the energy that the light will then possess. The energy that the light possesses is determined mainly by the frequency of that light. So the power of the light doesn't affect my frequency, which means it will not affect the energy of the photoelectrons. So now when the power is increased, we're increasing the number of photons that will be incident or that will hit the metal surface. When we increase the number of photons that hit the metal surface, we increase the number of photoelectrons that will be ejected from the same surface. The electrons will come off at the exact same speed as before, just that you'll have more of them, right? So that's why it doesn't affect the maximum speed, simply affects the number of photoelectrons that are emitted, but they'll all come off at the very same speed. Here's a shortened version of that. Increase in the power rating of the light bulb increases the intensity of the photons. That's your first mark. Increasing in intensity does not affect the maximum kinetic energy or maximum speed of those photoelectrons. Second mark. Super easy, super chilled. Let's jump to the next question. 10.3 then says, which one of the light bulbs, A or B, will produce the highest reading on the ammeter? Then we're asked to explain our answer. So when we look at the two, we need to think about what does the ammeter measure, right? So the ammeter measures current. What is current? Current is the rate of flow of charge. So basically, how much charge do I have going at a particular point or per unit time? Now, 1 electron will carry a certain amount of charge. 2 electrons will carry double that charge. So even though my electrons aren't necessarily moving through faster, but if I've got more electrons moving through per unit time, I'll have more current overall. So we can see that the one that will generate more electrons, which is bulb B, will generate a higher current. The simple answer you can give is to say light B, that's your first mark, because it has the higher intensity. Higher intensity means that more photoelectrons will be ejected and therefore more current, or your ammeter reading will be higher. There's your second mark. Very easy, 2 marks. Let's jump on to 10.4. 10.4 then says, calculate the, number 1, energy of the ultraviolet photons. Okay, now when doing this, we need to think about our energy equation for waves, right? So the energy equation is as follows. We've got E is equal to HF, or if we're not given frequency, we can write it in terms of wavelength by saying E is equal to HC over lambda. Let's quickly look at what we were given. We were given the wavelength being 490 nanometers. So let's jump in and solve that one quickly. Using the second equation, as we substitute, we can see that E is equal to H is Planck's constant. It's a constant. That is going to be 6,63 times 10 to the negative 34. We have to multiply that by C, which is the speed of light. The speed of light is 3 times 10 to the power of 8. And then we divide that entire thing there by the wavelength that was given to us. The wavelength was 490, remember, nanometers. So you have to convert, that's going to be times 10 to the negative 9. And if you take that and you plug it into your calculator, what you'll find is you get a final answer of 4,06 times 10 to the power of negative 19 joules. Super easy, nothing challenging. This question gives you 3 marks, 1 for the formula, 1 for substitution, and 1 for the final answer. Let's jump on to the final one. 10.4.2. It says we need to calculate the work function of the metal cathode, right? Now, looking at the work function, let's first start with the question of what is work function? Remember, the work function is the minimum amount of energy required by the metal to liberate electrons. So when the photoelectric effect happens, photons come down, they hit the metal. If they have enough energy, the energy that's required is referred to as that work function, then the metal will liberate electrons off there. So it's that minimum amount of energy required. How we can write this down now is to say, well, E is equal to HF. What is E? So E is the energy of my photon. That energy gets broken down into 2 components. The first part of it is going to be the work function, the energy required simply to emit or release those electrons in the first place. So that's going to be W naught. We refer to that as our work function. And anything that's left over is going to be energy that can be utilized by the electrons as speed, kinetic energy, essentially. So plus EK, and we refer to this as EK max because it's the maximum kinetic energy, right? The electrons will get emitted at very different speeds. What we care about is the maximum possible kinetic energy. Now that we've done that, we can go in and solve our question, right? So we need to find this work function underneath there. We already calculated E, that's this value right up in the question above, and then right there we need to then find the EK max. And to find the EK max, so let's look at the information that's been given to us. What we can see here, we were given the maximum speed, and then we can take that plus the mass of the electron, put that together to find our EK max. Let's jump in and solve the problem. So first of all, E, we'll substitute the value we got in above. That will be 4,06 times 10 to the negative 19, which is equal to work function. We'll leave that as W naught, is what we're trying to find in this problem here, plus EK max. Remember, EK is half mv squared. So we need to then add a half. What's the mass of an electron? This is going to be a constant, 9,11 times 10 to the power of negative 31. And then velocity squared. And we were given a velocity of 7.5 times 10 to the power 5. That's super fast. 10 to the power of 5. Don't forget to square it. And then we can simply solve for our work function. If you make W naught the subject of the formula, you'll find that W naught equals 4,06 times 10 to the negative 19 minus half 9,11 times 10 to the negative 31. And that is multiplied by 7,5 times 10 to the power of 5. Don't forget to square it. And if you plug that into your calculator, you should get an answer of 1,5 times 10 to the negative 19 joules. Super easy, 13 very easy marks. Remember, it is possible. Don't forget to join us for our prelim exam prep. We've got classes Mondays to Thursdays up until you guys write prelims. And if you need a private tutor, you want to have a lesson with myself or any of the other tutors you will see presenting lessons, give us a shout. Go to our website, book a free trial. We'd love to help you improve your marks. See you soon. Cheers.